In the previous chapters, we have applied the key concept of calculus, the derivative and the integral, to functions with one independent variables. So our function was in that form, y equals f of x, okay? This is one variable function. Actually, in this equation, there are two variables, x and y, but one of the variable is independent variable. Y is dependent variable, okay? So the graph of a such function is a curve in the plane. We know that. Symbolically, I will show that the graph like this one, y equals f of x. The horizontal axis represents the x, the vertical axis represents the y. So in this chapter, we extend the key concept of calculus to functions with two independent variables, okay? So y equals, or z equals, let's say, z equals f of xy. So now x and y are two different variables. These are independent. Okay. Now z is dependent variable. Dependent variable. Graph of the such function, two variable functions, are surfaces in a three-dimensional coordinate systems. So this is a two-dimensional r squared. This is two-dimensional. Now we have three-dimensional coordinate systems, x, y, and z value. So we will have some surface. Symbolically I show that this is z equals f of x, y. So for two values of the x and y, for example, so for the values of the x and y, this is x value, this is y value. So for that point, this is the domain of the function. You will find some z values, okay? So this is on the curve. So if this is x0, y0, this point is z0. So this point is x0, y0, z0. z0 here, f of x0, y0. In this course, we use the functions with two independent variables to study how production depends on the both labor and capital. How braking distance depends on both the weight and speed of a car. This is a very physical problem. Or how resistance in a blood vessel depends on the both its length and radius. So there are several applications for the two variable function. In general, the number of the variable can be 3, 4, 5, etc. So that's called a multi-variable function. But in this course, we will focus on just two variable case. In the following section of this chapter, in the fifth section as I remember, we justify the method of the least square and use the method to construct linear model regression analyze, okay? So least square is very important. The first term we use the regression analyze, you can remember. So now you will see the idea behind the regression analyze, which is called the least square method. Let us continue this section, the functions of several variable, by giving an example. You may recall in the first lectures of the first term, we introduced the concept of a function with one dependent variable. Now we broaden the concept to include the functions with more than one independent variable. A small manufacturing company produces standard type of the surfboard. You can remember this example. If fixed costs are 500, okay, 500 is fixed cost. And the variable cost is $70. So for each item, each product, 7 times X is the total cost. So this summation gives us the total cost, okay? You can remember this is total cost. This is fixed cost. 70X is the variable cost. You remember from the first term of this course. So here X represents the number of the boards produced per week. So the cost function is a function of a single independent variable X. For each value of the X from the domain of C function, there exists exactly one value of the C of X in the range of the C. Now, suppose that the company decides to add a high performance competition board to its line. Okay, so we have a company. Here, just we produce one board, okay, one product, surfboard. And now we add another product, competition board. Competition board. If the fixed cost for competition board is 200, the cost function is 200 plus, and the variable cost is 100 times X. Then the cost function of the competition board is that one. But the company, this is total cost for surfboard. That is total cost. Let's use different color. Total cost for computation board. So the total cost, exact total cost, total by considering these two products, total cost C of X equals summation of these two cost function. Okay, so 700 plus, but X represents the surface of the board, so let's change the X. Instead of the X, let's say Y. Y represents the number of the demand of the computation board. Okay, so here this is Y. So 700 plus 70X plus 100Y. Okay, so this is a total cost, but as you see that we have two variables, X and Y. Okay, we need another variable because the number of the surfboard and the competition board are not the same, okay, in the production. So this is a function of the two variables. So this is cost for weekly output of X standard board and Y computational board. Okay, let's emphasize X is the number of surfboard or standard board. Y is the number of computational board. In your textbook, generally it says standard board instead of the surfboards. Standard type surfboard. It's a computational surfboard. Both of them are the surfboard actually. So let's say this is standard surfboard. Actually, always this is board. So, but let's write standard. Standard surfboard. Here also, let's write standard. Okay. So this function is a two variable function. On the other hand, of course, as the company expands, its product line even further. Its weekly cost function must be modified to include more and more independent variables. One for each new product produced. If the domain of a function is a set of ordered pairs, then it is a function of two independent variables. Okay, in general, an equation of the form that one z equals f of x y, where f of x y is an algebraic expression in the variable x and y specifies a function. Okay, the variable x and y are independent variables. Don't forget, again, I would like to emphasize, these are independent variables. For example, there is no relation to produce the standard surfboard and the computational surfboard. Okay, there is no relation between them. X can be 5, y can be 10, for example. While x can be, when x is 5, y can be 20, 30, 50, etc. These are independent variables. And the variable z is dependent variable. Okay, this is dependent variable. The domain is the set of all ordered pairs. In the three-dimensional case, actually, let's look here. No, I wrote wrong that one. Okay, so this is three-dimensional in the R cube, in the space. So the domain here, some subset of the x and y. It can be negative or positive, but generally x and y represent the positive values. These are demands in this course. Okay, so this is the domain in the Cartesian coordinates, in the xy plane, and the graph is a surface, as you know. So there are some values. So this is our surface. Okay, this is our surface. Surface can behave some different shape like this. They show that. I mean, for example, this is the surface. Okay, this is the surface. F of xy is a real number. Okay, so and the set of all corresponding values f of xy is the range of the function. It should be noted, however, that certain conditions in practical problems often lead to further restriction on the domain of a function. As I said, x, y can be should be positive in your research area. We can similarly define function of three independent variable. Okay, we're not focused on this one, but this is three variable function, for example. So the graph of this function should be in the R4, so it is not possible to sketch the graph of this function. Okay, and this is three variable function. And also you can write the four variable function u equals f of w x y z. Okay, this is a four variable function. But you will not focus on these functions in this course. Let's turn back to the previous example. According to this result, we can say that the total cost, okay, let's write some things. So cost equals fixed cost of one product of the let's say first product plus variable cost of the first product, and we have another product, so fixed cost of second product plus variable cost of second product. And this idea can be generalized for also revenue. I mean, okay, let's write it here. I mean, for the revenue, as you know, the revenue is demand times price, okay? So demand for first product times price of the first product. Okay, so this is the revenue for the first product, but we have two products, so plus demand for second product times price of the second product. If we turn back the board question again, x is the, if you know the price function, okay, let's note by the p is the price of the standard board, let's note by the q is the price of the computational board. So according to x and y, we can write the revenue function, okay. So here let's p price of first item, first product, and q represent the price of the second product. So the revenue function, the revenue will be depends on the x and y or p and q, which depends on you. In terms of the x and y, let's write, okay. So here, if we have the price demand equation, x equals p of p equals x of p, sorry, price equals, let's note by the p of x, and price of the second item is q of x, okay. So these are the price demand equation. So revenue equals demand for the first product x times p plus demand of the second product is y times q. Here we should use the y because y is the number of the second product, okay, demand of the second product. So here let's say q of y. Q of y. So here x demand of first product, y demand of second product, okay. So here we can conclude this result, x times p of x plus y times q of y, okay. So this is a two variable function. For example, p of x, just let's write an example. P equals which form, generally these are linear, so let's say 2x plus 10, for example, okay. I don't know symbolic I wrote. For example, q is 3y plus, but when the x increase, price decrease, so this should be negative, I am sorry, minus 2x plus 100, let's say minus 3y plus 300, okay. Symbolically I wrote, I don't know the exact one. So by replacing these two functions, you can write the revenue function in terms of the x and y. So x times minus 2x plus 100 plus y times minus 3y plus 300. As you say, here we have x squared and here we have y squared. So this is a quadratic function. Generally it will be a quadratic function, okay. And also price here can be depends on the y, okay. So because of this reason, we represent the price function in terms of the both variables. So also this is a two variable function, okay. Let's step by step explain. So this price can be depends on the demand of the x first product and the second product, because one consumer can buy standard board or computational board. According to its price, they decide which board is better they ask, okay, and according to performance, of course. So always Sometimes maybe it can be depends on the one variable, that's possible, but in general depends on the two variables. So here p and the q are function of the x and y. Okay, this is xy, xy. So let's change our function. For the p, let's add the y here, for example. Let's add the 2x, for example. So here p and y inverse proportional, p and y is proportional. Okay, so this is constant is 1. So always this is constant is positive, I mean not 1, positive. Q, the increase of the demand for the second product decrease the price, but the increase of the demand of the first product increase the price. Okay, that is logical. So here our example will be this function. Symbolically I wrote in the lecture problem solving lecture, I will solve an example related with this situation. So it is possible to extend cost function, two variable, and revenue function, profit function, etc. And of course in the following steps, in the following sections, we will discuss the change with respect to revenue in terms of, we will discuss the change of the revenue in terms of the one of the demands, and in terms of the second demands. Okay, so we will discuss the derivative of the revenue with respect to x and with respect to y. Okay. In your textbook, you can find some example of functions of several variables for some physical geometrical problems. Okay, and in the problem solving R, we will discuss the Cobb-Douglas production function for the example for the two variable functions. Of course, we should talk about the three-dimensional coordinate system. So in the following records, I will discuss, or I will try to explain a three-dimensional coordinate system.